Welcome to our deep dive into torch.nn.CosineEmbeddingLoss. This is a powerful loss function that helps us learn meaningful similarity relationships in embedding space. Today, we'll explore how this loss function works mathematically, master its API and parameters, understand when to use similar versus dissimilar objectives, and see real-world applications in embedding learning tasks. We'll also visualize exactly how this loss guides our embedding optimization process. Let me show you the architecture overview. This is an image that illustrates how cosine embedding loss operates. We can see that it measures similarity or dissimilarity between two embedding vectors based on their cosine similarity. This loss function is commonly used in Siamese networks for face recognition, sentence embedding models, semi-supervised learning tasks, and general metric learning applications. The key insight is that it helps our model learn when two embeddings should be similar, meaning they point in the same direction, or dissimilar, meaning they should point in different directions. Now let's look at the geometric interpretation with another visual. This image shows us that cosine similarity measures the angle between two vectors, and importantly, it's independent of their magnitude. This property makes cosine similarity ideal for comparing normalized embeddings, where we care about direction rather than scale. When two vectors point in the same direction, their cosine similarity is 1. When they're perpendicular, it's 0. And when they point in opposite directions, it's -1. Let's start by importing all the necessary libraries. We'll need Pytorch and its neural network modules, NumPy for numerical operations, and Matplotlib with Seaborn for creating beautiful visualizations. I'm also setting up our plotting style and random seeds to ensure our results are reproducible. Here's a simple example to understand the basic usage of cosine embedding loss. Let me demonstrate the simplest possible example. I'm creating two embedding vectors. The first is 1, 2, 3, and the second is 2, 4, 6. Notice that the second vector is exactly twice the first, so they're pointing in the same direction. When we set our target to 1, we're telling the loss function that we want these embeddings to be similar. Let's calculate the loss and verify our understanding. Perfect. The loss is 0, which makes sense because these vectors are parallel, they have the same direction. The cosine similarity is exactly 1, meaning perfect alignment. And when we calculate the expected loss as 1 minus the cosine similarity, we get 0, confirming our understanding of how the loss works for similar pairs. Now let's look at the parameter documentation table. This shows all the parameters you can configure for cosine embedding loss. The margin parameter, which defaults to 0, controls the minimum distance between dissimilar embeddings. The reduction parameter determines whether we get individual losses per sample or a reduced scalar value. Let's explore how the margin parameter affects our loss calculation. Now I'll explore how the margin parameter specifically affects dissimilar pairs. I'm creating two embeddings with a known cosine similarity of 0.8 and setting the target to -1, meaning we want them to be dissimilar. Let's see how different margin values affect the loss calculation. Excellent, we can see a clear pattern here. With no margin, the loss is 0.8, which is just the cosine similarity. As we increase the margin, the loss decreases. When the margin reaches 0.8, the loss becomes 0 because the cosine similarity minus the margin equals 0. This shows that a higher margin makes the loss more lenient for dissimilar pairs, allowing them to have higher similarity without penalty. Let me visualize this margin effect with some detailed plots to make the concept even clearer. This visualization beautifully shows two key insights. On the left, we see how increasing the margin directly reduces the loss for a fixed cosine similarity. On the right, we see the loss surface for dissimilar pairs across all possible cosine similarities. Notice how higher margins shift the curve to the right, creating a larger dead zone where no penalty is applied. Now let's understand the different reduction modes and how they affect our output. I'm creating a batch of embeddings with mixed similar and dissimilar targets. Let's test all three reduction modes, none, mean, and sum, to see exactly how they transform our loss values. Perfect. With reduction equals none, we get individual loss values for each sample in our batch. With mean reduction, we get the average of those values, and with sum reduction, we get their total. This flexibility allows us to choose the most appropriate reduction for our training setup. Let's explore gradient flow and optimization dynamics to understand how the loss guides learning. Now I'll visualize how gradients flow through our loss function. I'm calculating gradients for both similar and dissimilar targets to see how the loss pushes our embeddings in different directions. Excellent, we can verify that gradients flow correctly for both target types. When the target is 1 for similar pairs, the gradients push the embeddings closer together. When the target is -1 for dissimilar pairs, the gradients push them apart. The gradient norms are identical, but the directions differ based on our similarity objective. Let me create a visualization showing these gradient directions as vectors, which will make the optimization dynamics much clearer. This visualization shows exactly how the gradients guide our embeddings. Note that the arrows shown are the gradients, which point in the direction of increasing loss. During gradient descent optimization, parameters are updated in the opposite direction to minimize loss. So for similar pairs, the actual updates would pull vectors together, while for dissimilar pairs, the updates would push them apart. Now let's move to training dynamics and see how we can learn meaningful embeddings. I'm creating a complete training example with structured data. First, I'll define a simple embedding model that normalizes its outputs. Then I'll create synthetic clustered data where samples from the same cluster should be similar and samples from different clusters should be dissimilar. This mimics real-world scenarios like learning document or image embeddings where items naturally group into categories. Let's train the model and watch how it learns to separate these clusters in embedding space. Fantastic results! Our model successfully learned to distinguish between clusters. The intra-cluster similarity reached 0.997, meaning items from the same cluster are nearly identical in embedding space. Meanwhile, the inter-cluster similarity dropped to -0.322, showing clear separation between different clusters. The overall separation score of 1.319 indicates excellent cluster discrimination. This demonstrates how cosine embedding loss can effectively learn meaningful structure from data. Let's visualize these training dynamics with comprehensive plots showing the loss curve, similarity evolution, cluster separation, and a 2D projection of our learned embeddings. These visualizations tell a complete story of successful embedding learning. The loss steadily decreases as training progresses. The similarity plots show same cluster pairs becoming increasingly similar, while different cluster pairs become dissimilar. The cluster separation score improves dramatically, and the 2D projection clearly shows 4 distinct, well-separated clusters. This is exactly what we want from an embedding learning system. Now let's look at a practical application with sentence similarity learning. I'm building a sentence embedding model that uses average pooling over word embeddings. This simulates how real NLP models learn sentence representations. The model takes token sequences, embeds them, pools them into a single vector, and normalizes the result. Let's train it on synthetic sentence pairs where some are similar, created by copying with small modifications, and others are completely different. Good progress. The model is learning to distinguish between similar and dissimilar sentences. The accuracy reaches perfect classification at step 15, showing that our embeddings can effectively separate the 2 types of sentence pairs. The final check confirms that all embeddings are properly normalized, which is crucial for stable cosine similarity calculations. Let's explore an advanced use case, showing how to implement triplet loss using cosine embedding loss. Here I'm implementing triplet loss by combining 2 cosine embedding loss calculations. We have an anchor embedding, a positive example that should be similar, and a negative example that should be dissimilar. By combining the losses for both pairs, we create a triplet loss that simultaneously pulls positives closer and pushes negatives away. Perfect! The triplet loss implementation works correctly. We see that the positive pairs have very low loss because they're already similar, while the negative pairs have 0 loss because they're already sufficiently dissimilar given our margin. The verification confirms that our positive example is indeed more similar to the anchor than the negative example, with similarities of 0.995 versus -0.25. Let's visualize the loss landscape to better understand how the loss function behaves. Now I'll create a comprehensive visualization of the loss landscape for both similar and dissimilar pairs. This will show how the loss varies with cosine similarity and margin values. These contour plots reveal the complete loss landscape. For similar pairs on the left, the loss is simply 1 minus the cosine similarity, creating a linear gradient that's independent of the margin. For dissimilar pairs on the right, we see how the margin creates a triangular region of zero loss in the lower left, where embeddings are already sufficiently dissimilar. Let's discuss common pitfalls and their solutions when using cosine embedding loss. I'll demonstrate 4 common pitfalls. First, unnormalized embeddings with different scales. Second, using incorrect target values. Third, setting the margin too large. And fourth, dealing with zero vectors. Let's see each problem and its solution. Great, we've identified and addressed all common pitfalls. Cosine similarity naturally handles scale differences, so unnormalized embeddings work, but normalization improves stability. Using wrong target values like 0.5 can produce unexpected behavior, so always use 1 or -1. A margin greater than 1 makes the dissimilar loss always 0, since cosine similarity ranges from -1 to 1. And zero vectors can cause issues, so add checks or small epsilon values to prevent them. Let me review the best practices summary. This section provides key recommendations for when and how to use cosine embedding loss effectively. We cover ideal use cases like embedding learning, similarity learning, contrastive learning, and few-shot learning. The key recommendations include always normalizing embeddings, using appropriate margin values, balancing your dataset, and monitoring both loss and similarities during training. Finally, let's run a comprehensive example that demonstrates all the key features we've learned. I'll create normalized embeddings with mixed targets, test different configurations, including various margins and reduction modes, and verify that gradients flow correctly through the network. Excellent, all configurations work perfectly. We've tested different margin values and reduction modes, confirming that the loss behaves as expected in each case. The gradients flow correctly without any NaN values, showing that our setup is numerically stable. This comprehensive test validates everything we've learned about cosine embedding loss. And that concludes our deep dive into cosine embedding loss. We've explored its mathematical foundation, mastered the API, understood the role of margins, seen practical applications from cluster learning to sentence embeddings, and even implemented triplet loss. You now have all the knowledge needed to effectively use this powerful loss function in your own embedding learning projects. Thank you for joining me on this journey.